Three, two, one. Okay, here we go. So, as promised, we are now going to see that matrices and linear transforms are very intimately related, and specifically what we're going to prove, ultimately, is that matrices are a very specific example of linear transformations, and there are a lot of linear transformations that are basically just matrices. Okay, so I do want to point out this is it looks like we got a lot of slides. I don't anticipate this being that hefty of a video, but there's a lot to talk about here. This is definitely this is juicy material, right? So we want to savor it. So a lot of slides, I guess. Okay, all right. So let us get to it. Okay, so recall that the thing that we're talking about right now are linear functions between vector spaces. So, right, these are mappings that respect scaling and respect addition. Equivalently, they respect linear combinations, right? So as we noted, if you want to prove something is linear, you can do them individually, but it's more efficient to do it this way. And in practice, I mean, this is typically how you always prove linearity, is verifying this. Very rarely do you actually need to rely on these to prove the scaling and the addition separately, because normally if you figure out them separate, why they work separately, there's nothing stopping you from kind of doing it all at once. But there are the occasional, like, ones where it's like, really, you gotta do scaling first and then do adding. Anyway, so something that we saw was that multiplying by a matrix is a linear mapping, right? We did a specific example with R2 to R2, but there's nothing stopping me from that being an m by n matrix, right? So note that the inputs come from Rn, and their outputs would be in Rm, right? This is an m by n times an n by 1. The output is m by 1. Okay. All right, and as I just said, every matrix multiplication is a linear mapping. It turns out that linear mappings between finite-dimensional vector spaces are basically multiplication by a specific matrix. And that's the main goal for today, is to prove that every linear transformation in the finite-dimensional setting is basically just multiplying something by a matrix. And that's it. So, in some sense, the reason we spent so long studying and playing around and talking about matrices is that finite-dimensional vector spaces, oh yeah, going full Uper there, okay, matrices basically completely take care of finite-dimensional vector spaces. And so today we're going to make that super formal using linear mappings. Okay. So the key ingredient to all of this is going to be the following result. And before we jump into it, I want to introduce a terminology, just so I don't have to write the word distinct a million times. So a set with n elements in it will be called an ordered basis if it's a basis for V and those elements are distinct. So this is the language that's usually used when you're talking about a basis that's been put in a list. People will say ordered, and what they really mean is that it's a distinct set. So I will stick to that so I don't say the word distinct a million times. I'll just say ordered basis. It's shorter than saying it's distinct and it is a basis. Just say ordered basis. Everybody knows what's up. Okay, so the big, and I didn't have a pause in there for some reason, but whatever. Great. It was already minute 3 and it's garbage. Right, so the big theorem we're going to prove is the following. If you've got an ordered basis and you got two vector spaces, you can always create a function so that the ordered basis maps to these outputs, and we can always do it linearly. So note, I didn't assume nothing about y1, y2, y3, all the way to yn. I don't care what they are. I can always linearly map the basis onto them. Right. So that is, on its own, a really striking theorem, right? The fact that the outputs can just be whatever the hell you want. You can make them all the same thing. It doesn't matter. Right? You can make them all 0. Freaking screw it. Have fun. Right? The fact that you could do this is really surprising, but once you make the first step, which I already spoiled, so if we've been looking at that, once you see what the first step is, it's really obvious what you're going to do. Right? Because it's a basis, that means I can find scalars so that every input can be written as a linear combination of the elements on the basis. And as we talked about, since you're a basis, we are linearly independent. That means those scalars have to be unique. So clearly the function I'm going to create is this one. Right, so the function, so that if you give me an input, there are unique scalars associated with the basis elements, while the outputs then are just going to be the linear combo involving the elements from y1 to yn. So once you make kind of that first step of like, oh yeah, by the way, since it's a basis, I have unique scalars I can always choose, the creation of this function is just like the obvious way of doing it. Right, but as we're going to see, it turns out that for linear functions, the actual formula we don't care about. We just care about where it sends basis elements. Okay, so what do we need to prove? We need to prove this thing that I created is actually linear, and then I also want to stress that it is a unique function. So we'll prove that it satisfies the conditions we want, and then we'll verify that any other function that does this is the same function. Okay, so first we'll verify that it sends the basis elements to where we want them to go. Okay, so fix a k. Right, then we can write the basis element as a linear combo of the basis elements where all the scalars are 0 except for the k spot where it's 1. And what does my function do? If you feed it in a linear combo like this, it spits out the linear combo and replace the basis elements with these selected outputs y1 to yn. Okay, well, all the scalars are 0 except at k when it's 1, so that will just give me yk. So, boom. That's easy. What's a little trickier is the following. We want to verify it's linear. Now, it turns out this isn't really so tricky, but more of just an exercise in management. Alright, so pick two scalars and pick two elements out of V. We're going to verify that we're linear, so we want to show that F respects the linear combo. So, since we have a basis, we can represent y and x in terms of scalars and the basis elements, like that. And note that if I were to then scale and add them up, it's going to look like this. Right? So, hey, there we go. That's how it's represented using the basis elements and scaling, and a b there instead of an n for some reason. B is right next to n. All right, yeah, you can't fault me on that one. Okay, let me go fix it. Where is it? There it is. Alpha sub b. Honestly, I've done that repeatedly, and I thought I caught all of them. And anyway, there we go. It's cleaned up now. Okay, so when I apply my function f, remember the way I defined it was to spit out the scalars, replace the b1s with y1s, replace the bn's with yn's. So when I feed this into my function, it does exactly what I just said, replaces the b1s, the b2s, the b3s to the bn's with y1s. See, if I was just lazy and copied and pasted it, it would have went a lot smoother. Anyway. Alright, so now we just pull everything apart accordingly. Right, so there is an alpha times alpha 1 y1. There is an alpha 2 alpha times y2. So all the way down to alpha n. Same thing for the betas. And, right, so we can just group and pull everything apart the way we want to. Right, here we're really invoking the commutativity of the addition and the fact that the scalings can be moved around how I want them to be moved around. But what do we know? Well, this is what f of x is equal to. That's what f of y has to be equal to, since x is a, right, alpha 1, b1, all the way to, oh, I'm missing a plus sign. Oh my god. Alright, do a quick update on that. Boom. Got it. Alright. Anyway. Alright, so yeah, beautiful. We've got that the function f is linear. It sends the basis elements to the selected outputs, the y1s, the yn's. The last thing I need to do now is verify that it's actually unique. Oh, hey, it shows unique. Alright, so let's say you've got a function, it's linear, and it sends the basis elements to the selected outputs, y1 to yn. Take anything out of E, it's a linear combo of the basis elements, and then just feed it into F and feed it into G. Right, G is assumed to be linear, So it respects the linear combo, and it's assumed to spit out the B1s to the Y1s, the B2s to the Y2s. So, hey, we get that. And as F was constructed, F does that exact thing. So, F has to be G, it's unique. All right. So, we have verified now that if you have a finite basis, you can always create a linear function, right? So again, let's look at the assumption here and really stress the power of this. And I'm gonna freaking put the pause in now. Oh god, oh no, oh boy. I deleted something I wasn't supposed to. Alright, there we go. There we go. Should have done this before, but whatever. Yeah, anyway, so, right. This tells us now that the construction of linear mappings is super easy. Just take a basis and then just tell me where the basis needs to go, right? As this shows us, it does not matter where you send basis elements. You can, wherever you want, just throw them there, right? So this is really powerful. This tells us how to create linear functions, right? Right, we're basically able to make linear functions out of nothing, more or less. You just need to establish a basis, and then boom, you've got any sort of linear function that you could possibly imagine. Okay. Alright, so, like I just said, this result is incredibly powerful. I can't even begin, right? I can't even begin to really get into how important linear functions are, but this particular result is incredible, because it allows you to just create linear functions that just do really neat things. So, a quick consequence of this is the following. If I've got a vector space V, and it's got an ordered basis with n elements in it, there's a unique linear function that sends those things to the standard basis, right? So note, as I said, the output of this function can be whatever you want. Just pick n things. So, naturally, when you want to actually invoke this result, you'd be really clever about your choices. So if you choose them to be the standard basis elements, note what we just did. There is a unique linear mapping that sends the basis elements of B to the standard basis elements of Rn. So in other words, we finally have formally demonstrated it. This tells me that every finite dimensional vector space literally is Rn. There we go. So there was a good reason we started out this entire course just playing around with Rn and studying Rn and seeing things that Rn could do, because every finite dimensional vector space is Rn in disguise, right? Because you can take that ordered basis, there is a unique linear transform that matches up the basis, so there you go. That function respects the scaling and the addition, the key ingredients of linearity, and it sends the basis elements to the basis elements. So every finite dimensional vector space, it's Rn in disguise, right? And we can formalize this even more explicitly, because given a vector space with the ordered basis, this unique linear transform usually gets a name. What I'm going to call it is the standard coordinate transformation with respect to the basis B. Because this tells you that if I take an element, its output, f of y, this lives in Rn. And we call this the standard coordinate vector for V with respect to B. So in other words, this output here is exactly the representation of the element in V as it would be in Rn. Right? So every finite dimensional vector space is Rn, and this gives us the linear way of creating elements in Rn to be the faithful representation of things out of Y. V, sorry, not Y. Okay. So let's do some quick proofs. So let's say you've got a vector space with an ordered basis, then the standard coordinate representation, this element of Rn, has to be the scalars so that x lines up with, and I'm missing another plus sign. I swear, I miss that L dot plus thing. So as you're learning LaTeX, or if you are, you don't have to. I think it makes things easier. And by it makes things easier, I think it's got its stuff with it. And sometimes I always with the L dots, man, I always forget the plus. Anyway. Okay, so what we're going to prove now is that this transformation of a finite dimensional vector space into Rn, we can kind of go back and forth at will. So in other words, the representation of X in terms of Rn, it has this representation in terms of V. So it's precisely the things that scale up and give you X. And then next up, the ordered, the standard vector representation is unique. So in other words, if I have a standard representation, there's only one thing in V that gives me that. Okay, and then in other words, that means if I've got a distinct set in V, the corresponding set in Rn is also distinct, which might be important for, I don't know, linear independence. Okay. Alright, so quick facts to prove here, and these are just going to be totally just unraveling of definitions. So suppose that we've got our representation of X in terms of Rn. As V is a basis, that means X can be represented as a linear combination for some vectors out of the reals, right? Now, what I want to prove is that those vectors are actually these ones in this standard coordinate vector there. Okay. Well, the standard coordinate vector, that is the output of the standard coordinate transformation, which is linear. So if I feed it in a linear combo, it respects the linear combo. The standard coordinate transformation takes the basis elements and lines them up with the basis elements of Rn. So there you go. We know that this is alpha 1 to alpha n, and that's literally this right here. So the betas and the alphas have to be the same. Right. This is an element in Rn. The first entry is beta 1, the second entry is beta 2, all the way to beta n. So alpha 1, alpha 2, alpha 3, all the way to alpha n. They're all equal. Okay. Nice. And conversely, let's say you've got X as a linear combo. Well, like I just said, the coordinate, the standard coordinate transformation is linear. So, and look, another freaking alpha B. Oh my god. I am gonna bust the gasket, I guess. There we go. Update that. These slides are going to be pristine once I get done with them. Anyway. Alright, yeah, so there you go. The standard coordinate transformation is linear, so it respects the linear combo, and then just gives me that, yep, you had those scalars alpha 1 to alpha n, they go where they need to go. Alright, so the next two things is, let's say we've got coordinate representations. Well, every X can be represented as a linear combo of elements out of the basis, and as we just proved, that means that the coordinate vector for X is the element in Rn with those entries. Now note, I'm representing it here as a vertical column instead of a horizontal one. As I've said, it doesn't matter how you write them, we're always talking about the same thing. So this tells me that the coordinate vector for Y is this, and applying and another alpha B. Oh boy. I swear, right? Because there's the BN too, and it's just like butterfingers all around. Where's the oh jeez, alright. There you go. There we go. Alright, anyway. So, because Y's coordinate vector coincides with this, that means Y has to be the linear combo of the elements beta 1 to beta n using those, so X and Y have to be the same. And now that we've got that, the distinctness is super straightforward. Pick two things here. By part B, I know that the vectors have to be the same, and since that was a distinct set, that means the indices have to be the same, so the set of coordinate transforms, coordinate vectors, that has to be distinct as well. Okay. So a couple of quick little facts. We'll use these here and there. It's worth establishing. Let's look at a specific example and get a better feel for how this works. So we set it up. We did a couple of proofs. Let's make it a little more concrete. Okay. So as we've talked about, the set of polynomials is a very nice basis. The power functions. If we wanted to be careful about a domain, we would specify a subset, but we can just assume the domain's all real numbers. Who cares? This means that if we were to cut it off at any spot, that has to be a basis for all of the polynomials whose degree is less than or equal to n. Okay, so this is a very common vector space to look at. It's a very important one. It's very useful when it comes to approximating functions. And I will talk a little bit more about least squares approximation a little later on. So it's a very important set for a variety of reasons. Now note that it's a vector space with a basis that has n plus 1 things in it. And these are specifically called the standard basis. And again, note that the dimension for the set of polynomials of degree less than or equal to n, so all of the polynomials that can be written as linear combos of those, this is actually an n plus 1 dimensional vector space, right? So even though there's an n here, it's actually n plus 1, right? Because this is technically t to the 0th power. So we start counting at 0, which is wrong. And yeah. All right. So, hey, here's a basis for a vector space. Let's play around with coordinate vectors. Okay, so let's get a good feel for how coordinate vectors work. So if we take the standard basis for P3, you note that the coordinate vectors are precisely what you think they should be. Right? 1, 0, 0, 0, 1, 0, and 0, 0, 1. That should have a sub B next to it. A lot of ooh, this some sloppy slides today. Jeez, so I apologize. But all right. Now, equipped with that, any coordinate vector can be pretty easily put together. So, for example, the coordinate vector for the polynomial -1 plus 2t minus 3t squared, well, the coordinate transformation, so here, note B is representing the standard basis for R3. Right, well, this mapping is linear, so it respects scaling and additions, and bing, bang, boom, there you go. So its representation is exactly what you think it should be, -1, 2, and -3. Okay, so this is, keep in your mind, this is the example when we're going on and talking about coordinate vectors and playing around with them, because in reality, this is what they are, right? Polynomials are a great way to think of them. Now, speaking of that, we called it the standard basis. That means there's probably other bases out there, right? Same thing for Rn. We've talked about the standard basis for Rn. I bet that means there are other goofball bases out there, right? We've talked about a create basis for Rn by just creating appropriate matrices whose columns are linearly independent. And it turns out we can basically do the exact same thing for any finite dimensional vector space. So for an example, we are going to prove that that set is a basis for P2. Okay. This basis actually has a name. It's called the Chebyshev basis for P2. There are Chebyshev bases for all order of n. They start getting a lot more involved. And it turns out that they're better at something called polynomial interpolation than the standard basis is. There are a lot of functions that you can approximate using polynomials, and it turns out that if you use the standard basis to do the approximation, that falls victim to something called Runge's phenomenon. Oh god, I don't know why I couldn't get that out. Basically, it turns out that if you use the standard basis for polynomial approximation, they end up being a little too wiggly, and you get these bad numerical approximations. So it turns out that Chebyshev polynomials, in fact, are the best ones when it comes to approximating functions. So when you're trying to do some numerical stuff, you usually use the Chebyshev bases rather than the usual bases, because they're as great as they are, and you know that they can approximate functions, they actually kind of do a crap job of it. But anyway, so here's the question then. How do you actually prove it's a basis? Right, well, we can prove that it spans a set and that it's linearly independent. That's one way. We can also note that, well, P2 is a three-dimensional vector space. I have 3 elements here. If I just verify that these are linearly independent, then there you go. But note, I'd have to verify their linear independence as functions. We've spent a whole bunch of time talking about matrices, and we know how to check matrices, and we know how to check in Rn how to be linearly independent very quickly by just smashing them together, getting a matrix, and just doing its determinant. It'd be great if we could do that for P2, but, right, those are functions. Those aren't Rn. We can't make a matrix. Or can we? So, let's say you've got a vector space with an ordered basis, and you've got a distinct collection of things so that the output is linearly independent. So the corresponding set of coordinate vectors is linearly independent. Now note, because we started with a distinct set, the output was distinct. Here we go, using those results we just proved. Then this set has to be linearly independent, right? And this is classic unravel the definitions. We want to prove the set's linearly independent, hit it with some scalar, set it equal to 0. The coordinate mapping is linear, so it respects everything. It sends the 0 element to the 0 element. These are assumed independent, so the hypothesis guarantees that all the scalars are 0, so boom, that set is linearly independent. Okay, so the power here is that I can now verify linear independence inside of a vector space by looking at the appropriate representatives in Rn. Right, that's really great because in Rn, linear independence is super easy to check. You just set up your matrix, and the linear independence of the columns of that matrix is equivalent to the matrix being invertible, which is equivalent to 1,000 things. So this is great. So in dealing with abstract vector spaces, we can work with independence now solely in terms of Rn. That's great. Okay, and let's see this theorem in action. So I'm now going to easily easily verify that this set must be a basis for P2. It's got 3 things in it, so I just need to verify that it's linearly independent. As we discussed, we know that it must be a basis, then it must span the set. So take the standard basis. Note that the coordinates with respect to the standard basis for the Chebyshev polynomials are as follows. So, these can be represented as follows there. Now, that matrix that you can form by gluing these all together has a determinant of 2. So, this set is in fact linearly independent, right? This collection of things in R3. The matrix formed by gluing it all together is linearly independent. That tells me this is linearly independent, and since it is the same size, it must be a basis. There we go. Boom. So I now know that's a basis for P2. So I know that every polynomial in P2 can actually be written as a linear combination of those 2 polynomials. Right. That's really nice, right? And it just boiled down from convert everything over to be in terms of Rn. Really neat. Neat proof. Okay. Now, since it ensures that it's a basis, that means I can talk about coordinate vectors with respect to that basis, right? So note, this would be an element of R3, but the basis now is different. Right, so this isn't going to be just -1, 2, -3. That's if it was B. That's if it was the standard basis for P2. This is a new basis for P2. Right, note that we used the standard basis to prove that this basis, the set was a basis. So that's another reason why it's called the standard basis. It's the one that you use to verify other sets need to be bases. Okay. So how do we compute this? So now what we're trying to compute, we're trying to find the scalars so that I can represent this as a linear combination of those things, which means if I move everything around, I want this polynomial to equal that polynomial, which means I need those coefficients to be equal, and those coefficients are equal is equivalent to, oh look, a matrix equation with, oh look, this exact matrix that we were just talking about, the right-hand side being the coefficients right here. I wonder if that always happens. Alright, so, yeah, oh boy, it's like there's some, super deep theorem about linear transforms having to be bases, having to be matrices or something that we're going to prove in a little bit. Beats me. Anyway, so the problem of finding the coordinate vector with respect to this basis turns into just solving this matrix equation, right? Now note that this is a super easy one. In fact, this is a very easy set of a very easy system of linear equations. You can just back solve this right away. But if this was significantly more complicated, you now would row reduce and go from there. So we quickly see that C is -3/2, B is 2, and then from this equation, A is -5/2. So the coordinate vector for the polynomial -1 plus 2t minus 3t squared with respect to the Chebyshev basis is -5/2 to -3/2, right? And you can check that that's right by scaling the elements of the Chebyshev basis, 1t, t squared minus 1, by the respective coordinates, and when you add everything up, you get the thing that's on the inside. So, here we go. This is exactly how coordinate vectors work with respect to a basis. Okay, and now you know. Okay, right, so as we just saw, there's a connection here to a matrix. Okay, well, let's get to the star of the show for today. Okay, so the first thing we're going to prove is that every linear mapping from Rn to Rm can be represented as matrix multiplication. We want to do this first because the full-out theorem that every linear transform between finite-dimensional vector spaces is a matrix, it's a lot easier if you do this first, because then basically we're going to get it for free. So here's where we actually have to do the work. And by do the work, I mean we have literally nothing to do. Okay. So I want to create a matrix, and here's how we're going to do it. Let the matrix A be the matrix whose columns are precisely these elements. Okay, so we have n of them. These are elements of Rm, so they have m things in them. So I have m rows and n columns, and this is the basis for Rn. Okay, note that everything in X is a linear combo of the standard basis elements, and when I apply T to this element here, T is linear, so it respects the linear combo, and oh hey, look, you get this linear combination of these elements here. These are the columns of that matrix A. That means the matrix times X is literally this linear combo, and boom, there we go. We found a matrix that does exactly what I wanted to do. It took 2 lines. Oh boy. Nice. Okay, right, so we've talked about this before, where matrix multiplication is really a vector equation in disguise, right? A matrix equation is a system of linear equations, which is a vector, linear combination of vectors. Here we see it coming back again to help us out. Okay, so we found a matrix A that works. How do we know it's unique? Okay, now note, it's an n by n matrix, so we actually have to be a little clever here. If this was an n by n matrix and we knew it was invertible, it's for free. There's nothing to do. You can just multiply both sides by the inverse. Right? If they're invertible, we're just done. This is a rectangular matrix, though, not necessarily a square one. So we have to be a little clever about how we prove the uniqueness. Okay, so it's only to verify that the matrix A is unique, so let's say I've got another matrix that does exactly what I want. So in other words, the linear mapping is represented as matrix multiplication. So the key ingredient here is to note the following fact. Multiplying a matrix by the standard basis elements gives you the columns. And that shouldn't be surprising. Actually work out a couple of examples of the multiplication there. For any p by n, no, not even an m, any p by n, if you multiply it by the n by 1 column standard basis element, you'll be picking out the columns. Well, oh boy, what do I know about A times a vector? I know that that's what T of that vector is equal to, which I know is that's what B is a vector to. So this equation tells me that A and B have the same columns. So they're the same matrix. And that's it. Nice. So there we go. We have now proven that every linear transformation from Rn to Rm is an m by n matrix in disguise. Okay, so this matrix is usually referred to as the standard matrix. This would indicate there are other matrices. We'll talk about that in a moment. And it's a unique matrix satisfying that equation. Okay. Now, how do you find this? Well, by the proof, we just need to figure out what the linear function does to the basis elements, right? And we've already seen that repeatedly today. If you know what a linear transform does to basis elements, you know everything you need to know about the linear function. All right. So for an example, let's say I've got a mapping from R2 to R3 that sends the basis element 1, 0 to 7 pi square root of 2, and then sends the other one to 0. Right, so first of all, we know there's a linear function that does this, and we know it's unique. And now, this becomes the first column, this becomes the second column. There's the matrix, the standard matrix for that linear transformation. There it is in all of its glory. Nice. So if you want to figure out the standard matrix for a linear mapping, just look at what it does to the basis elements. That gives you the columns for the matrix. It's really neat. Now, if somebody wanted to be a supreme jerk to you, they would say, here's a linear mapping, and it sends two elements somewhere that are linearly independent, so they form a basis. And then you would need to use that information to figure out where they send the standard basis vectors. Totally not a problem that I put on your problem list. That I actually did it as an exam problem in 207 the last time I taught it, and nobody was a fan of that problem. So, I hope you enjoy it. Okay, so what's left? Alright, well, now we know that every linear transform from Rn to Rm can be represented as a matrix. Now that we've got that, we can prove the full-out theorem, that every linear transformation between finite-dimensional vector spaces can be represented as a matrix, but as you can see here, the representation can be a little bit convoluted. So you take the standard basis for Rn, the standard basis for Rm. So note here that I'm using U1 to UM instead of E1 to EN. Some authors are super lazy with this, and they'll do E1 to EN and then E1 to EM, and you're supposed to understand that, well, these E's are in Rn and those E's are in Rm. I'm going to be nice to you. In the last video, I complained about how terrible our textbook is. I want to complain again. They prove this first, and then they use this to like get all the other stuff I just did. So they did everything backwards. It's like the dumbest way to do it. Like to the point where I'm like, it had to have been done purposefully, but I still have no idea why they did it that way. But anyway, so we're now going to prove the full-out version of the theorem we just proved, that every linear mapping between Rn and Rm is a matrix. Every linear mapping between finite-dimensional vector spaces is a matrix. It's a little bit more of a pain to figure out what the matrix needs to be and how to use it. Now, it is worth noting that this matrix A, you can use this, so if you were to take non-standard bases for Rn and Rm, this gives you a matrix, and you would usually call that the matrix with respect to these bases, so, yeah. Anyway, so how are we going to prove this? So, how do we prove the result for Rn and Rm? Well, we fed in the basis elements into the mapping T, and we looked at it there. So we want to do the same thing here. We'll feed in the basis elements in the T, but note the basis elements we need to feed in the T are B1 to Bn. So, as we proved, if you know where basis elements go, you can create a linear mapping. So we'll feed the basis elements into T. Those live in W, and with respect to H, they have coordinates. And we can create a linear mapping from Rn to Rm then by sending the basis elements of Rn to these coordinate vectors in Rm for the output of T with respect to B. So, yeah, as you can see, there's a lot of hoops you need to jump through. Now, that linear transformation has a standard matrix. That matrix is the one we want. Okay, so how do you prove it's the one we want? Well, we want to prove that it satisfies this. So that's what we're going to do. Okay. All right, pick something out of V. B1 to Bn is a basis, so I can represent it as a linear combo. And note that the standard coordinate vector for B has A1 to An as its entries. The linearity of T means that when I feed X into it, it's going to respect all the linear combos. Now, I'll apply another linear mapping to this, the coordinate transformation with respect to H, so turning these elements, which are in the vector space W, which is a copy of Rm, right in the skies, if you apply the coordinate transformation, the standard coordinate transformation, well, it's linear, so it respects all of these. What do we know about the T1B1 with respect to H? Well, that's f of E1, all the way down to f of En. What do we know about f of e1? Well, we've got its standard matrix representation. We know that that's a times e1. I can now factor a out of the whole thing, and now we've got this linear combination, but this is precisely the vector that's got alpha 1 in the first spot, alpha 2 in the second spot, all the way to alpha n, so it is x, and there we go. That is indeed the matrix we're looking for. All right, so this one is super slick. This is like this is a well-oiled machine. They have all these parts that we set up, and you just put them all together. All right. But we're not done. We need to prove that it's unique, so how do we do that? Okay, well, suppose there's a matrix that works. No, I can't use B. I've already used B for something. All right, and it's the exact same argument where we're going to multiply it by the standard basis vectors to get the columns to line up. And note that the thing we need to plug in now, though, is the basis for V, right? Because, again, remember, the basis elements for V, they line up with the basis elements for Rn. Okay, and then there we go. We've got B times the standard basis vector lining up with C times the standard basis vector. So as we know, B and C then have to be equal because they have the same columns. All right, so there we go. We have now proven that every linear mapping between finite dimensional vector spaces is a matrix in disguise. Getting this matrix is not super hard, but you got to jump through a couple hoops to get it. So let's wrap things up today. Let's finish off with a nice, interesting application of this result. So let's take the mapping from the polynomials of degree at least 3 to the polynomial no more than 3 to the polynomials of degree at most 2. And this linear transformation specifically is take the derivative, right? If I have a polynomial whose degree is no more than 3, its derivative has a degree of no more than 2. Note that it's linear, right? As we already discussed, differentiation is a linear operation. If I feed in the basis elements for P3, 1t, t squared, and t cubed, then I get the following. I get 0, 1, 2t, and 3t squared. The standard coordinate vectors for these are 0, 0, 0, because there's nothing, 1, 0, 0, 2, so 0, 2, 0, 3t squared, so 0, 3t. So note that this is a 3 by 4, right? Because I have a mapping going, all right, yeah, 3 by 4, okay, lining up. The matrix formed by slapping them together is the matrix for that linear mapping guaranteed by the previous result. So if you've got a linear mapping, what you do is you feed in the basis elements for your vector space, the domain, then create the standard coordinate vectors for their outputs. Then you slap that together, and that gives you the matrix. So now, note here, like hilariously, this tells me that differentiation is really this matrix, which is a fun thing to say, right? So the derivative is really just a matrix in disguise. It's kind of neat. And in fact, you can check that that is actually differentiation. So multiplying a vector by this is the same thing as differentiation. Let's see that in action. This is really cool. So take a polynomial. How about this one? Negative 1 plus 2t minus 3t squared plus 4 3t. Note that its standard coordinate vector is negative 1, 2, negative 3, 4, right? That's an element out of P3, so that's its standard coordinate vector there. If I multiply this by that matrix, I get that vector right there, 2, negative 6, 12, which is the standard coordinate vector for the derivative. Right, take the derivative, you'll get 2 minus 6t plus 12t squared. That is silly. That is so cool. So here we go. Differentiation is actually matrix multiplication in disguise. That's really neat. Now note, huge asterisk next to that. In the finite dimensional case, it's that. In the infinite dimensional case, differentiation, trying to represent operators as infinite matrices in the infinite dimensional case, that's whack, let me tell you. So we'll dive into that maybe in the bonus content week. But anyway, there you go. All about matrices and linear transforms. So when we're dealing with vector spaces, and they're finite dimensional. They're really just Rn and Rm in disguise. So then there are ways of using that information to help us out, as we just discussed, and as you will see in your exciting new problem list. So that's it for me for today. So what's next? Well, what's next is to talk now a lot more about dimension and linear transforms, and we're going to prove a big theorem connecting the two. All right. That's it for today. See you next time.